Hi, I'm Brendan, and today I'm going to talk about how to add a calling convention, and I'll take RISC-V Vector as an example. Okay, so for the agenda, I'll first give a brief introduction to calling convention, then I'll talk about the RISC-V Vector and its stack layout. And lastly, I'll dive into the implementation detail in LLVM. Okay. So what's the calling convention? Basically, calling convention is the protocol between caller and callee, and it defines some rules for caller and callee to communicate smoothly. In physical machines, there's no any call instruction that has arguments. The way for two subroutines to pass the arguments is through registers or memories, and the rules of passing argument is defined by calling convention. So for example, let's say we have a function performing multiply and add. And in this function, it calls subroutines to do the multiply and add respectively. For calling multiply, we need to place the arguments which are A and B in some places like registers or memories, and multiply then read those input from the same registers or memory to perform computation. And these rules are all defined in calling convention. Same for calling the add function. Okay, so calling convention also defines the set of registers for return value. When returned to the caller, both of them also need to know which registers or memory to use. Okay. During procedural call, some registers might be clubbered. When using registers after the call, we need to make sure the data is consistent. So calling convention also defines a set of registers that need to be saved either by caller or by callee. Okay, let's talk about RISC-V ABI and stack layout. So RISC-V has three different kind of data registers, which are integer registers, floating point registers, and vector registers. And first, we have 32 integer registers named x0 to x31. We also have aliases for each register to make users easier to identify the purpose of them. And register in the red box are what we are focused in today's talk, which are argument registers and callee saved registers. So there are also 32 floating point registers. 12 of them are callee saved registers and 8 of them are argument registers. So before we dive into the stack layout, let's talk more background about RISC-V Vector. RISC-V Vector is a scalable vector and its length is defined by each hardware. In RISC-V, there are 32 vector registers, which is same as Intel's AVX and ARM's SVE. Each of them is in VLAN bits. There's also one CSR called VLAN-B in RISC-V Vector to hold the vector length in bytes. For example, if the vector length is 128 bits and VLAN-B would be 128 divided by 8, which is 16 bytes. And RISC-V has a vector V-type CSR for recording configurations such as 11 width, computation policy, and vector register group multiplier, etc. Okay, so the image illustrates the difference of vector register arrangement for standard calling convention and vector calling convention. The reason we need another calling convention other than the standard calling convention for vector is that in some applications or libraries, they don't really use vector register heavily. On the other hand, the latency for vector loads and store instructions are high. So it's better to have another choice for other usages. The upper image is the standard calling convention, and the lower one is vector calling convention. The main difference between these two calling conventions is calling safe registers. In standard calling convention, all of vector registers are caller safe, which means it's caller's responsibility to keep the register state across procedural calls. However, in vector calling convention, V1 to V7 and V24 to V31 are callee safe. They are only saved if the callee need to occupy any of them. And every function maintains its own memory space during the call, which is known as call stack. Here is the stack layout of RISC-V. As you can see, there are 5 sections in total. From top to bottom, we have callee allocated area for variable arguments, scalable callee safe registers, scalable local variables, RISC-V objects, and variable size objects. And I'll describe them in detail in following slides. First, we have scalar callee safe registers and scalar local variables. Let's say we have a simple function which with a local variable declared. The assembly of the code is in the middle block. And the first line in the block adjusts the stack down for preserving all of registers. Then we have scalar callee safe registers starting from SP -16 and scalar local variables starting from SP -20. The relative position on the stack is shown on the rightmost picture. Next, we add a RISC-V local variable. The size is calculated by reading the VLAN B CSR and multiplied by 2. This is placed right below scalar local variables. There's one thing to mention is that RISC-V objects section contains not only vector local variables, but also vector callee safe registers. Callee safe registers are placed right below the vector local variables. Okay, then we have variable length argument. Here we save all of the arguments in pre-allocated area, no matter they are used or not. This is not only for access simplicity, it also releases those registers for register allocator to lower the pressure. Okay, the next section is variable size object. Some local variable size are unknown during compilation. For example, an array with size defined in other objects. We need to get the variable from symbol table to calculate the exact size. And the size need to be 128 bits aligned, which is specified in the spec. And so here is the code snippet in the purple box to calculate the exact size during runtime. First, it reads the variable from symbol table and shift left by 2 since it's an integer type, which is 4 bytes. Then add 15 followed by an I instruction to ensure the offset is aligned correctly. Okay, so those are 5 sections of RISC-V call stack layout. Okay, let's talk about implementation details. To enable calling convention, we need an attribute to pass the information from front end to back end. And there are some files need to modify to get it work. The first file is called attribute.td. And this file gathers all of the attributes with different aspects. For RISC-V vector call, we need to define an attribute for declaration and function type. The keyword in C or C++ and some other front-end information are also described in this section. We also need to define an enum in specifiers.h. This is used to keep the information in client side for all other following functions before backend. We also need a way to map the calling convention attribute from frontend to backend. In cgcall.cpp, we have a function called client callcomp to LLVM callcomp to do the mapping job. Okay. We also need to define an enum in the calling conv.h. This is used to keep the information from LLVM IR all the way down to machine code. And the LLToken.h file defines vector calling convention keyword in LLVM IR. And the token would be parsed by LL parser and convert to corresponding calling convention enum in LLVM. On the contrary, the ASM writer emits the corresponding keyword in LLVM IR for each calling convention enum. Okay, for now, we know how to add an attribute keyword for the calling convention in both CLAN and LLVM. We are also able to make the LL parser recognize the calling convention keyword in MLIR. So let's take a look at a test case to see what we've already done in the previous slides. In the upper image, we have a bar function declaration with RISC-V Vector CC. Then we make a call to the bar function in the test function. And the generated LLVM IR is shown in the lower image by running the command clan-target RISC-V64-S-emit LLVM. And you'll see the RISC-V vector vector CC attribute is correctly lowered to the LLVM IR from front end. And it will be later used by selection deck to determine the mechanism and the set of registers to lower the calling convention. Okay, next we are going to talk about RVV specific concepts for vector registers. The first one is called ELMO, which stands for Vector Group Multiplier. For example, the leftmost image illustrates ELMO equals 1, which means the data occupies only one vector register. However, in the middle image, where ELMO equals 2, it means data occupies two vector registers. And this is one of flexibilities in RISC-V where users have full control over resources in terms of vector registers. And the second concept is called NF, which is short for number of fields in a segment. This is basically used in segment load store instructions that need multiple register group to be consecutive. In the following slides, we'll use RVV type to represent vector type with only ELMO, and we'll use vector tuple type to represent the vector type with both ELMO and NF concept. Okay, there are also constraints for those two vector types in previous slides. For RVV type, we have a group of registers. The first constraint is that starting registers should be multiple of ELMO. And the second constraint is that all registers in a group should be consecutive. In example 1, we have ELMO equals 2, and we have V2 and V3 for this type, which is valid. Since the starting register is V2 and is multiple of 2, and V2 and V3 are also consecutive. However, in example 2, although V1 and V2 is consecutive, the starting register is not multiple of 2. And on the contrary, example 3 is invalid because the registers in the group should be consecutive. Okay. And the constraint for tuple type, vector tuple type, is based on RVV type with an additional constraint, which need all of the groups to be consecutive. In other words, all of NF times Elmo registers should be consecutive. In example 4, the type has Elmo equals 2 and NF equals 2. So the starting register should be multiple of 2, and all 4 registers should be consecutive. However, in example 5, it's invalid because it breaks the consecutive rule for all of the groups. So an important question is how do we model RVV type and tuple type? For RVV type, we already have V-scale in LLVM to model it. For example, let's say we have V64M1 for representing I64 RVV type with Elmo equals 1. And it is modeled as V-scale times 1 times I64, since each block is 64 bits in RISC-V. This is same as how ARM models SVE. However, there are no existing mechanism to model the vector tuple type. Let's say we have a type V64 M2 times 4, which has Elmo equals 2 and NF equals 4. One possible way to model it is through the same way as RVV, which could be something like V-scale times 8 times I64. However, this approach would be ambiguous between the type V in 64 M2 times 4 and V in 64 M4 times 2, because the total number of vector registers is the same. So we are not able to identify whether it's Elmo 2 NF4 or Elmo 4 NF2. SVE also has NF concept, but it doesn't have Elmo, so the current mechanism is sufficient for SVE. And originally, we used structure type to represent the vector tuple type, where NF is mapped to the number of elements in the struct, and each element is of scalable vector type with specified Elmo. For example, a vector tuple type with Elmo 2 and NF4 is represented as a struct type with 4 elements, and each element is an Elmo 2 scalable vector. However, this approach has a potential problem. In selection deck, the struct type is flattened to its element type, where the group information is gone. So it's not possible to inference its exact type. We need a new type for handling vector tuple in RISC-V. So fortunately, LLVM has a built-in type called target extension type that has type arguments and also integer arguments. In vector tuple type, we use type argument to encode Elmo information and integer type to encode NF information. The Elmo info is represented by scalable vector type with 8-bit integer as its base element. And NF is represented directly by its value. And it's obvious that RVV types can be directly lowered to scalable vector MVTs, which are introduced by SVE. However, in RISC-V, we introduced new MVTs for vector tuple types. During instruction selection, target extension type is converted to its corresponding MVT with Elmo and NF information. For example, V in 64 M2 times 4 is lowered to MVT type, which is RISC-V underscore n times 16 I8 times 4, which only contains Elmo and NF information, but eliminate element type information, which is trivial to backend. And each MVT also has its register class, that each register class is mapped to a set of registers constructed by rules we just discussed earlier. Okay, so in the next few slides, I'm going to show you how to deal with the RISC-V Vector Calling Convention in the backend. One thing to mention before we proceed is that all of the registers are allocated by general register allocator, except for those related to calling convention. We have to implement the rule in each backend to specify the physical registers for input argument and the return values. So what we need to do first is to define the set of registers that are managed by callee, which are also called callee-safe registers. In RISC-V Vector Calling Convention, we have V1 to V7 and V24 to V31 in callee-safe register set. We also need to add the super registers such as V2, M2, V4, M4, V24, M8, etc. Because different register group uses different instruction for load store. For example, to store only a single V2 register, we use VS1R, which means store 1 4 registers. However, to store V2M2, which is V2 with Elmo equals 2, we need a VS2R to handle it. If we don't add V2M2 to the register set, backend will decompose V2M2 to two Elmo equals 1 vector registers and use 2 VS1R to store it, which is not expected and optimized. Then we need to implement the target hook get callee-safe regs to determine the live-in and live-out registers in a function, to tell caller whether to store those registers or not. In this case, we don't need caller to save and restore those registers. Only callee needs to save and restore them when using any of them. Okay, and this is the utility function to collect all of callee-safe information that need to be saved in this call. Before spills and reloads, we need to assign an offset for all the registers that need to be saved in the call stack. We also need to align each frame. In our case, A-byte alignment. For RISC-V register, it has fractional Elmo, which means the data would occupy only a portion of the vector register. However, for simplicity, we always want the object size to be at least 1 vector register, which is 8 byte in RISC-V modeling. And one thing to mention is I'm also working on an optimization to try to make the vector register spills to store only valid data. And in other words, if it only occupies a fraction of a register, and we don't necessarily need to use the 4 register store instruction, we can use other lower overhead instruction instead. Other benefit is that we don't need to allocate a 4 vector register size in the call stack for those objects if it doesn't use all of the space. Okay, this is the target hook that emits the actual instruction for spilling register. Likewise, we also have a restore target hook for the stack slot. Let's see what changes we've made. This is a simple test case that has an inline assembly call with 2 clubbered registers, V1 and V8. In standard calling convention, the caller is responsible for keep all of the vector registers state during procedural call. So the %VA is originally placed in V8. When it enters the function test vector standard after the inline assembly, it needs to make sure the data is consistent. So we can see there's a register move instruction before and after the call to act as spill and reload. And if we apply calling convention keyword, which is RISC-V Vector CC, to the function, V1 becomes a calling safe register, which need to be saved by test vector calling when calling the subroutine. So there's another few lines of code in the red box that handle the spills of vector registers. Once the set of registers for each class are defined, we need to define 3 other target hooks, which are lower formal argument, lower return, and lower call. Basically, we just need to use CC state to help with that. I'll show you the register set in the following few slides. So this is the RVV register set. We need to define all of the registers that includes every elmo and from V8 to V23. So we have elmo 1, elmo 2, elmo 4, and elmo 8. For vector tuple type, the NF information is separated using underscore, and it also defined in the same file. Okay, sometimes the arguments number are greater than the number of registers, which means some arguments are not assigned to a physical register. For those that are not handled yet, we need to make them pass by reference, which is basically storing data to the stack and pass the stack address by using general purpose registers. Okay, so in the first test case, we are able to see that %x and %y are passed by V8 M8 and V16 M8 respectively, and as we expected. However, in the second case, it ran out of registers. So %x1 and %y1 are passed by registers, and %x2 and %y2 should be passed by reference. The 4 register load instructions in the red box are used to read them back from stack. Same mechanism applies to vector tuple type. The definition of registers already model the constraint, so we can just handle them in the same way. And same for vector tuple type running out of registers. Okay, so let's conclude what we have today. We have a brief recap of calling convention, and we have an introduction to RISC-V Vector ABI. We've learned about RISC-V stack layout, and finally we dive into details of implementation, including adding function attribute and handling function arguments and handling caller safe and callee safe registers. Yeah, that's my content today. Thank you.
Thank you, Brandon. Any questions?
Yeah, thank you for the talk. Is there anything else, like as a part of this process, that you could do within TableGen? Or is it, I believe you're just defining the registers used?
Yeah, actually we can define the how to lower the calling convention in TableGen. And I know that ARC64 or some Intel stuff do the same thing, but in RISC-V, we haven't do that. I mean, maybe there's some historical reason, and we have some special rules for RISC-V. So currently, we don't move to table gen yet.
Thank you.